Hello everybody, welcome back to the online course on computer organization and architecture. So, we are in the first module is based on your fundamental of digital computer and we are in the unit 2 digital logic building blocks. Now, we are going to see what are the things that we are going to cover in this particular unit. So, as we mentioned that we are going to first mention about the objective. Let us see what are the objective that we have today. So, in this particular case we have mentioned 3 objectives. Objective 1, illustrate the behavior of digital system. Again we are going to cover these things in knowledge level, because these are the things that we will be needing while going to discuss about computer organization and architecture. But if you look into the objective, so if we are going to look for the behavior of digital system in another course, say digital logic design. In that case, these objective may go into either analysis level or maybe in the design level. But here we are just going to touch upon it and we are going to give the information in knowledge level, and we will be using this knowledge while discussing about the fundamentals of computer organization and architecture. Objective 2, describe the working of basic building blocks of digital system. So, here we will slightly give ideas about the analysis of the digital system. And objective 3, explain the issues related to sequential circuit. Okay, we will come back to this point, what is sequential circuit. Now, we are talking about digital computer, or this module is fundamental of digital computer. When we talk about digital computers, necessarily another question will come to our mind, whether is there some other computers are there. So, in that case we can look into this issue and we can say that yes, we can categorize the computer in two broad categories. One is your digital computer and second one is analog computer. Here in this particular course we are mainly going to emphasize on digital computer. What is a digital computer and what is analog computer? So, these computers are electronic devices. So, it works on electrical signals, that signals may be either voltage or current. So, in case of analog computer we work with continuous signal. Just say that if I am going to draw a behavior, say some time, and in this particular case say if we are having that voltage V, in x axis we are having time and y axis say we are having voltage. So, this electrical signal varies continuously, then we say this is your analog signal. So, in case of analog computer we are going to work with continuously varying signals, but in case of digital computer we are going to sample these things, that signals in particular instance of time, and we are going to look for those signal values only. So, as for example, I can have some timing instance. I can say what is the signal value at time t 1, what is the signal value at time t 2, t 3, etc. So, in this way we are going to look into it. That means, we are going to work with discrete signals. So, digital means discrete signals. So, when we are going to talk about digital computer, here mainly we are going to concentrate on 2 level of signals, either at some time instance the signal is high or in some instance the signal is low, something like that. So, in T 1 signal is high, T 2 signal is low, T 3 signal is high, again T 4 signal is high, like that. So, for sampling these things basically we work with a clock signal. So, basically we are having a continuous running clock and we are going to sample the signals at some instance of time, say maybe somewhere here. Okay. And secondly, I am saying that we are going to work with discrete signals and we are going to see the voltage values at some instance of time. So, these voltage values may be either high or low. Okay. So, in some cases we represent it by H or low. And generally when we talk about high voltage, basically it is depending on the technology, it may be something voltage more than 5 volt, in some cases it may be 8 volt, in some cases it may be 12 volt. And for low means it is basically 0 volt or maybe a very low voltage which is less than say some 0.7 volt or something like that. So, if voltage level falls below this particular level, generally we say that this is your low signals, and when voltage level goes above some certain value, we say that this is high level. So, generally we represent these two states as high and low. For our convenience, that high may be represented by 1 and low will be represented by 0. So, basically it is a combination of zeros and ones only. At some instance of time, the signal value is high, that is represented by 1, and in some cases the signal value is low, in that cases it is represented by 0. So, eventually we are getting some signals value which is your say 0, 1, 1, 1, 0, 0, 1, 0, something like that. So, finally, what will happen? We are coming down to some number system which is your binary number system. So, in our discussion mainly we are going to concentrate or going to discuss with respect to this binary number system. So, digital computer works on binary number system. In top level we can say like that, but in low level we will say that it will work on either some high voltage or some low voltage. So, this is the way we can look upon the digital computer. Again, this digital computer is basically related to digital logic. So, in case of logic, generally we are having two truth values, one is called true and second one is called false. So, true is represented by T and false is represented by false. So, in some places what will happen, 1 will be represented by your true and 0 will be represented by false. So, eventually all are going to have the same meaning. So, in case of digital computers, we are going to work with discrete signal. Values of discrete signal may be high or low. High values will be represented by 1 or true and low values will be represented by 0 or false. Now, what is a digital circuit? So, in case of digital circuit, we can say that any digital logic function is represented by Boolean expression. So, if we write some Boolean expression, that Boolean expression is going to evaluate some function and that function can be implemented with the help of your digital logic circuitry. Again, the digital logic circuit can be categorized into two different categories. One is your combinational circuit and second one is your sequential circuit. So, in that particular case, I will just simply say that I am going to take a digital circuit and going to just think it as a black box. I do not know or at least what is inside that particular point. So, here we are going to give some input signal say I 1, I 2 to say I n, and we are going to get some output signals. Okay. These output signals depends on the input signals and depending on the behavior of the circuit, we are going to get the values of those particular output signals. So, such type of circuit is known as your combinational circuit. So, that means the output entirely depends on my input. This is a combinational circuit. But when we talk about the sequential circuit, then what will happen? Some of the output will be given as a feedback and treated as an input to the circuit. That means, the current output of the circuit depends on my previous output. That previous output is coming as an input to my circuit. So, in that particular case, we are going to say this is the sequential circuit and output depends on the previous output also. So, we have to have some mechanism to retain this particular previous output and we will see that particular things when we are going to talk about sequential circuit. Now, there is a correlation between Boolean expression and digital logic. Just say that I am simply talking about simple function say a b plus a c. So, this is a Boolean function and a, b and c are Boolean variable. That means, it can take values either true or false. On the other hand, I can say that true can be represented by 1 and false will be represented by 0. So, if we are having such type of Boolean expression, for every Boolean expression we are having a digital logic circuit. So, how we can implement? I can say that this is a and b, it says that these values of this particular component is 1 provided both a and b are true, or both a and b are 1, then the values is 1. Again, this function is having two components a b and a c. This is the OR combination or plus combination. It says that the functional value will be 1, either A B is 1 or A C is 1. So, that means we are going to talk about two operations, one is your and second one is your OR. For such type of operation, we are having digital logic gates. So, in this particular case, what I can say that? I can say that I am having an AND combination, 2 AND combination, and I am having 3 input A, B, C. So, it is basically A and B is ANDing together and A and C is ANDing together. So, when both A and B and A and C are true, then what will happen? The output of these two gates are going to be high or true. Now, main final function is the OR of these two combinations. So, we are going to connect one OR gate over here, and finally, this is the functional value f. So, these are the AND gates, 2 AND gates and 1 OR gates. So, this is a circuit and this circuit implements this particular Boolean expression. Now, you can say that now I have already mentioned that I can bring these particular internal details as a black box, and whenever I am going to give the input over here, depending on the input we are going to get the output. So, this is the behavior. Now, we will see what are the different types of logic gates we have. So, logic gate basically we are having some standard gates, and here in this particular course we are going to see in the gate level only. How those particular gates are implemented, we are not going to look for it. That implementation issues will be discussed in some other courses, maybe in your digital circuit design. So, here first gate is your NOT gate. What is that NOT? It says that if my input is high, then output is low, and input is low, output is high. So, A is your input and X is your output. So, when A is 0, X is 1, when A is 1, X is 0. Second gate is your AND gate. So, in AND gate already I mentioned that if both the inputs are high, then output is high. So, this behavior is represented with the help of a tabular fashion, and this table is known as your truth table. So, basically the behavior of digital circuit can be represented with the help of truth table. So, here I am having two input A and B. So, when both the inputs are high, then output is high, otherwise output is 0. So, you just see this combination, when both are high, then output is high, in other cases output is 0. Similarly, we are having a NAND gate. NAND gate is nothing but AND and invert. So, first we are going to ANDing the operation, this is AND, then this bubble is going to talk about the inverted. So, we are going to say this is the NAND gate. So, since NAND is the invert of your AND, so you just see the truth table, the output is exactly inverse of this particular output of AND gate. When it is 0, then output is 1, and when output of AND gate is 1, then output of NAND gate is 0. Like that, we are having OR gate. In case of OR gate, either A or B. If any one of the signal is high, then output is high, otherwise it is 0. So, you just see that if both the input are 0, then output is 0, but if any one of these input is high, then output is high. Similarly, we are going to get a NOR gate. NOR is nothing but OR and invert. So, first we are having the OR combination, then this bubble again represent the invert. So, you just see that OR is inverted over here. When output of OR is 1, then output of NOR is your 0. So, NOR is invert of this. Like that, we are going to have another function called XOR. It is called exclusive OR. So, in case of OR, if any one is high, then we are going to say the output is high. But in case of XOR, we say that output is high provided either of them is high. So, in that particular case, say if both are high, in that particular case output is 0. So, either of them A and B is high, then output is high. So, similarly, XNOR is nothing but the invert of XOR. So, exclusive OR and exclusive NOR. So, you just see that functional value is just invert of this particular XOR gate. Now, you just see that here I am just mentioning some of the gates, like that we are having other gates also. So, in that particular case, that NOT, it is an unary gate, we are having only one input, and depending on that we are having the output. But other gates are your binary gates, because we are having two inputs. Depending on this input, we are going to have output. So, now you just said that we are having two inputs. Now, here I have cited some of the examples, and how many such type of gates we can have if we are going to take two inputs. So, it is basically we can have several combinations, and if you look into all those combinations, say these are the four different possibilities that we are having, either both are 0 0, 0 1, 1 0 and 1 1. These are the only possible combination for two input gates. So, we are having four possible input combination, and for this four possible input combination, what we can say that either all outputs are 0, all outputs are 1, or maybe some of them are 1 and some of them are 0. So, in that particular case, you can say that we are going to get total 16 different combinations. That means, 16 different function or binary function can be implemented if we are having two inputs. Now, secondly, these gates can be extended for more inputs even. Say, if I am going to look for a gate where I am having 3 input over here, so 3 input AND gate. So, this gate can be visualized like that. First, I am going to have AND combination of first 2, and secondly, the whatever output we are getting, that will be combined with the third input. So, like that we are going to get the effect of 3 input AND gates, or maybe 3 input AND gates can be implemented with the help of electronic circuit. So, this is possible because these particular operations are associative. That means, A B dot C is equal to A B dot C. So, since it is associative, so such type of expansion is always possible. Now, we are talking about this particular logic gate. Here we are having two terms called complete set of operators, and I think you may be knowing about these things. So, the complete set of operators are your nothing but AND, OR and NOT gate. If we have these 3 gates, then all other gates can be implemented with the help of these 3 gates. As a simple example, you just see that if I am going to talk about this particular XOR gate, what is the behavior? If 0 and 1 output is 1 and 1 and 0 output is 1. So, that means what I can say that it is basically nothing but B inverse A. So, this is B is 0, A is 1, at that particular point the output value is 1. Similarly, either B or A inverse. So, this is nothing but this expression is going to give me this particular XOR combination. So, now just see, if we do not have this particular gate, then what will happen? With the help of NOT, AND and OR gate, I can have the effect of this particular gate. So, this is B inverse, A inverse, we are using this particular NOT gate, then B inverse dot A, that means we are using this particular AND gate, we are having 2 AND combination and they are now combined with this particular OR gate. So, you just see with NOT, AND and OR, all circuits can be implemented. So, that is why we are going to say that this is the complete set of operators. Along with that, we are having another terms called universal gates. So, NAND and NOR are treated as universal gates. Why you say these are universal gates? Any digital logic circuit can be implemented with the help of only NAND gate or only NOR gate. So, this is the things that we are having, that is why we said these are the universal gate. Now, as an assignment, you just think how to implement this particular function with the help of only AND gate, NOR gate or NAND gate. Just take it as an assignment and just see how this circuit can be implemented with the help of only NAND gate or with the help of NOR gate. Now, we are going to see some of the building blocks that will be used while constructing our computers. So, one thing is, first circuit I am going to talk about here is your half adder. This is basically adding of 2 numbers, and these are the addition of binary numbers, because we can represent only 0 and 1, that is all. High voltage means 1, low voltage means 0. In that particular case, the behavior of half adder can be represented with the help of this particular truth table. So, we are having 2 input A and B and 2 output sum bit and carry bit. S represent for sum and C represent for carry. So, this is basically when both A and B are 0, then my sum is 0. When A and B is 1, then sum is 1. When A is 1, B is 0, then sum is 1. And when A is 1 and B is 1, I am going to get sum as 0, but it is going to generate a carry called 1. So, this behavior for S we need one circuit, for C we need another circuit. Just look into the behavior of S. Here we are going to say that this is nothing but the exclusive OR. So, that means this exclusive OR gate is going to give me the behavior of sum function, and if you see that C, it is nothing but AND combination. When both are 1, then output is 1. So, in that particular case, this AND gate is going to give me this particular carry function. Now, here I am talking about the half adder. When we talk about the half adder, necessarily that something will come to your mind, that means there may be some other adder also. Just see, this is an adder circuit which can add a single bit number. Now, just consider about some 3 bit numbers. Then what will happen? We are going to add it, say 1 and 1 is 0, and it is going to generate a carry 1. Then 1 and 1 we are going to add together, then output is 0, and it is going to generate 1 carry. Now, 1 0 and 0 is going to give me 1. So, this is basically the result is your 1 0 0. Now, first bit is fine. You just see that if I am going to give A and B, I can get the sum bit, along with that I am going to get the carry bit. But when I am coming to that next bit, now what will happen? You just see that I have to take decision that functional value or output of this function depends on 3 inputs. That means, we have to take care of both the input A and B, along with that the carry that is coming out from my previous bit. So, for that we are having another circuit, we call this is the full adder. So, in case of full adder, now you just see that we are having 3 input A, B and carry in. That carry in is coming from the previous bit position. So, it is coming from here and we are going to get this carry in. And when we add them together, it will generate a carry out like this one. So, we are having this particular carry out. So, the behavior of this circuit can be represented with the help of this particular truth table. Now, since we are having 3 inputs over here, so total input combination will be your 2 to the power 3, which is your 8. So, this is the maximum number of combination that we have. So, we have cited all those possible combination over here, and depending on the behavior of addition, we are going to find out what will be the my output function. Now, once we have this particular output function, then we can implement with the help of this particular circuit. Now, you just see that now this complete circuit will be treated as my full adder, and finally, once we give the signal over here, say 1 1 0, finally, we are going to get the output as your 1 and 1, sum is 0, carry is 1. Now, we have to see one more things. Now, say these are some logic gates or electronic component. When we put signal 1 and 1, immediately we are not going to get the result over here, because these electronic components are having some delays. It needs some times, and that time, whatever time it is required, we say this is the propagation delay of that particular block. Here we are simply using an exclusive OR gate. So, this XOR gate will take some time to give me the final stable output over here. So, once we get a stable output, then only we can work with this particular second gate, because 0 is coming, Cin is coming immediately as soon as I am giving the input, but the second input to this particular XOR will come after some unit of time only, which depends on the propagation delay of this particular gate, and this second gate will also have some propagation delay. So, finally, we are going to get a correct result. So, this time we have to consider, and we are going to say that the final output we are going to get after some amount of time once we give the stable input, and this time depends on the propagation delay of the components of that gate. So, that means to get the result of a full adder, it is going to take some time. We have to consider that particular time also. So, this is the internal circuit. So, as a block representation, we can say that this is full adder. I am having 2 input A, B, along with that we are having that carry in, and it is going to give me two outputs, sum bit and carry bit. So, this is the block diagram, but what is there inside this particular full adder? If you look into it, we are going to have this particular circuit only. Now, we know or we have seen the behavior of half adder and full adder. Now, if you are going to construct a 4-bit adder, then how we are going to construct it? That means, we need to add 4 bits. So, that means, we need 4 adder, or here we can use the full adder even. So, what I can say that this is my 4 full adder. So, here I am having 2 input A0, B0, A1, B1, A2, B2, A3, B3. Now, what will happen? This first full adder is going to give me the sum bit, and along with that it is going to give me one carry out also. That carry out will go as a carry into the next full adder. So, this is your S1, and it will go, that carry out will go as a carry in. This is your S2, this is your S3, and along with that I am going to get one carry out also. Since least significant bit is not having any carry input, so that carry input bit will set to 0. On the other hand, this full adder can be replaced by a half adder also. Now, this is the 4-bit adder. Like that, if I need an 8-bit adders, I can cascade 8 full adder and going to get the circuit. Now, you just see I am talking about the propagation delay. Now, this full adders is having some propagation delay. Once I am giving this A0, B0 and C in, it will check sometimes, and we are going to get the output over here, and along with that this C bit we are going to get. Now, I am giving this 4-bit numbers, say 1 0 0 1 and 1 1 0 0. In that particular case, or I can say that second full adder cannot perform its job immediately as soon as I am giving A1 and B1. It needs to wait for the stable output in this particular carry out of the first full adder. Once we are going to get the stable output, then only this particular second full adder can perform its job. So, like that second full adder is going to give me some output, the third full adder need to wait for that particular stable output. So, in that particular case, you just see that if the propagation delay of the first adder is some time t, then total time that required to get a correct output of this full adder will be maybe your 4 times of t, because second full adder is going to give me the correct result after t unit of time. Second full adder is going to give me a stable output after 2t time. So, like that it is taking the 4t time. Now, like that if we are going for an n bit adder, that means the total propagation time will be your n t, where t is the propagation delay of one full adder. So, you just see that nowadays we are talking about say 32-bit computers, 64-bit computers. That means it will take lot of time to give me the output. So, for that simple circuit we are not going to use. For that we will use another circuit, modification of this particular adder circuit, which is known as your carry load ahead adder. So, here we are not going to discuss about these things, just as an information I am giving you that we are having another circuit where it is known as your carry look ahead adder, and carries will be generated at the same time and simultaneously it will be propagated. Okay. Carry generation and carry propagation. So, carry look ahead adder. So, with the help of this carry look ahead adder, we can reduce this particular propagation delay of the adder. So, this is some bit of information I am giving you. So, that or if you are interested, then you can just look for any book on digital logic where adder has been discussed thoroughly. Now, the second circuit is your decoder. We are having another building block called decoder. here we are having n input lines and m input output lines, and the m, whatever m output lines we are having, this is basically it is less than equal to 2 to the power n. So, if we are having n input lines, maximum output lines we are going to get as your 2 to the power n. And what is this circuit behavior? Depending on the input combination, only one of the output line is high. Okay. So, here you just see that we are having 3 by 8 decoders, we are having 3 input lines and we are having 8 output lines D 0 to D 7. So, this 3 input lines A, B, C. Now, what will happen? Since we are having 3 input lines, so what will be the total number of input combination? This is your 2 to the power 3, this is equal to 8. Depending on one combination, generally one of the output line is high. So, basically what will happen? When both are all are 0, then D 0 is high. When that one signal is high, that C is high, in that particular case I can say that D 1 is high. Like that, when all combination is 1, then we say that this is your D 7 is high. So, depending on the input combination, only one of the output signal is high. So, this decoder we are going to use for selecting some of our requirements or some of our functions. So, if we are having some choices that at that particular instance of time we have to select only one. In that particular case, we are going to use this particular decoder. So, this is a 3 by 8 decoders, like that we are going to get n by 2 to the power n decoder, where n is the input line and 2 to the power n is the output lines. And this particular decoder, in most of the cases we are having a signal called enable signal. E n is nothing but enable. That means, when this enable signal is high, then only it is going to behave like a decoder, otherwise it is not going to work, maybe all output will be 0. So, this is with enable line we are going to have a decoder. Now, this enable line helps us to construct some of the decoder. Say, if we are having a decoder, say I am having with me say 2 by 4 decoders, and I said that I am having, it is having 2 input lines A and B, but I need a say 3 by 8 decoders. Then what I can do? I can use 2 by 4 decoders. So, these are the output lines, 4 output lines we are having, and these are the 4 output lines that we are having for the second decoder. So, total 8 output lines we get. Now, here in both the cases I am going to give A 0, A and B and A and B. Now, depending on this particular A and B, say now A and B is having 2 combination only, 4 combination 0 0, 0 1, 1 0 and 1 1. When input say I am giving say 1 and 0, then what will happen? This particular line of say D 3 of this particular decoder and D 3 of this particular decoder will be selected, because this is the combination. Now, we have to select one of these 2 outputs. So, for that what will happen? We need another input, say I am having this particular C input. Then what we are going to do? We will use an inverter and put these things over here. This is the enable line and this is the enable line over here. Now, you just see that when I am having C, when C is equal to 0, then what will happen? You will see that we are going to, this is C equal to 0. So, enable line is 0 over here. So, we are not selecting this one, since C equal to 0. So, here I am going to get 1. So, in that particular case we are selecting this particular decoder, that means we are selecting this particular decoder output line D 7 and all these things will be 0. Now, similarly, when C is equal to 1, again I am going to get 4 combination. So, C 1 0, then what will happen? In that particular case, since C is equal to 1, here I am going to get 0. So, we are not selecting this particular 4 lines and we are selecting only that particular D 3, and it is nothing but now we can say that this D 3 is going to act as my D 6, because we are going to have from D 0 to D 7. So, like that we can use a decoder, or say we can use multiple decoder to construct a bigger decoder, and it is possible due to this particular enable lines. Now, we are having another circuit called encoder. So, encoder is the reverse of decoder. In case of decoder, we are going to decode from n line to 2 to the power n line. In case of encoder, we are coming from 2 to the power n lines to n lines. So, total we are having 2 to the power n input lines and we are having n output lines. So, this is a 4 by 2 encoder. So, depending on this scenario, now we are going to say either A 0 or A 1 will be high. Now, what we can do, say when I am going to say that this is y 0, y 1, y 2, y 3. Now, at any point of time, say any of one of the input line is high. So, this is basically say I am having this particular pattern, or maybe this is. So, these are the 4 inputs. Then what basically I can say that this is your. So, this input says that I am having 4 inputs. Now, depending on that I am going to encode it, and in that particular case I can say that this when y 0 is 0, we will say that it is going to represent 0. So, both A 1 and A 0 will be 0. When y 1 line is high, then in that particular case we will say that it is going to represent 1. So, this will be your 0 1. When y 2 line is 1, then it may be represented by 2, and when y 3 line is high, it is represented by 3, binary 3. So, this is the way we can encode it. So, encode is reverse of your decoding circuitry. So, here we are having 2 to the power n input lines and we can get n output lines. So, here what happens, we are just discussing those things in block level, how to implement it. These are very simple combinational logic circuit. You can take any book on digital logic and you can see the how it is done, and this is a very simple circuit. I am telling you, with the help of NGET it can be done. So, this is encoder. Like that, another building block we have, which is known as your multiplexers. So, it is basically going to multiplex or masking some of my input signals. So, it is basically like that, we are having several signals. At any point of time, we are going to take only one signal out of those particular n possible signals. So, here it is something like that. If we are having an input signal, we are going to put it to one output signal. So, it is called n by 1 marks. Now, how we are going to select it? For that we need some select line or control lines. That control lines depends on this particular number of input lines. If we are having n input lines, then number of select line will be your log 2 n ceiling of that. Now, we will see these things with a small example. Say I am talking about a 4 by 1 marks. Now, we are having 4 input lines I 0, I 1, I 2 and I 3. Depending on my requirement, we are going to take only one of this particular input signal and going to put it into the output signal, which is known as your masking the other signal and going to put the in one particular input lines to the output line. To select this particular 4 input, what happens? We need some select line or control line. So, here we are having 2 select line S 0 and S 1. So, we know that 2 to the power 2 is equal to 4. That means, depending on the combination of this particular 2 select line, we are going to select one of this particular input line. So, basically I can say that this is your S 0, S 1. So, what is the combination of those particular select line? That may be 0 0, 0 1, 1 0 and 1 1. Now, what will happen? Depending on this particular select line, what will be the my output? We are going to select one of this particular input signal. So, say that when S 0 and S 1 is 0, then I can say that we are going to select that input line I 0 and it will be transferred to the output side. When it is your 0 1, then I 1, then 1 0 I 2 and 1 1 is your I 3. So, this is the behavior of multiplexer. From n possible input signal, we are going to select only one out of those n signals. So, that is why what is the input, output and select line relationship? We are having n input lines, we are having one output lines. To transfer any one of these particular input lines to the output lines, we need select signal or control signal. What is the number of control signal? It is your log 2 n ceiling. If we are having 8 to 1 marks, then what will happen? We need 3 select line, because 2 to the power 3 is equal to 8. So, this 3 select line will have combination from all zeros to all 1, 8 possible combination. So, we are going to select any one of these particular input lines and going to put into the output. So, this is a multiplexer circuit, again it is a combinational circuit and very simple circuit. Another one we are having demultiplexer, which is the reverse of your multiplexer. So, here we are having one input line and we are going to transfer it to any one of those particular output lines. So, if we are again, I can say that input line is your 1 output line, and then what is how many select line we have? Again this is your log 2 log n to the base 2 select. So, we are having one input lines, now we are having 2 select lines. Depending on those particular select line, we are going to transfer this input line to any one of those particular output lines. So, again I can say that if it is your S 0 and S 1, that we are having that 4 combination, and depending on that what is the output line. So, here input will transfer to y 0, here y 1, y 2 and y 3. So, we are having one input signals, and now that will be transferred to any one of these particular output lines. So, this is demultiplexer. So, in computer we are extensively going to use those particular building blocks to construct our computers. Another unit we are having called arithmetic and logic unit, ALU. This is the basic processing element inside our computer, which can perform some arithmetic operation and logic operation. So, this is your block diagram. We are not going to see what is there inside this particular ALU. Just say that we are having some circuit, like that we are having a adder circuit. If it is an n bit ALU, that means both the inputs are of size n bits and the result is also n bits. That means we are having an n bit adder. Already we have seen how to construct an n bit adder. Similarly, what will happen? We may have several operation over here. Just I consider that I am having say addition operation, I can have subtraction operation, I can have multiplication operation, and so I am having division operation. So, I am having 4 processing element which can perform the operation addition, subtraction, multiplication and division. So, these are the say 4 arithmetic operation that we have. Along with that, we may have some logical operation also, logic operation also. I can say that I may have that AND operation, OR operation, or maybe say XOR operation, or maybe I can say another one say NOT operation. So, in this particular logic operation, AND or XOR are your binary operation, but NOT is an unary operation, because it is going to invert one of the inputs and going to get the output as the invert of this particular input. Now, you just see that like that, this is the processing element, and I am having 4 addition, 4 arithmetic processing element and 4 logic operation. At any point of time, we are going to perform one of these particular operation. Now, what operation we are going to perform, that will be given by these particular signals. So, depending on that signal, we are going to get the result, and along with that we are going to get some status also. Some of the status bit will be given, or some more additional control signal we are going to get, and that will be set or reset according to the behavior of this particular circuit. So, this is ALU is a basic building block, or it's a basic processing element that we are going to use in our computer to perform some of the arithmetic operation as well as some logic operation. So, now just say that how we are going to construct it. Now, if I say that this is the ALU, I am having these 2 input and bit input, and say this is basically I can say that this is A, this is B, and here I am going to get n bit result, and say that I am having those particular processing element. These are the 4 addition, subtraction, multiplication and division. Similarly, 4 logic operation, just say AND, OR, XOR and say NOT. Now, at any point of time we are going to give 2 inputs over here A and B. and we are going to perform one operation, and depending on the operation we are going to get our result. Now, how we are going to select this particular operation? Now, we are talking about in the previous slide, we are saying that we are going to get opcode, and here we are having some status line. One of the status line maybe I can say about that carry out. Okay. Like that we can have several status. Now, select any one of this particular input operation, we need the appropriate signal. So, for that what will happen? I can use 8 different signal. So, this is your 0, 1, 2, 3 like that up to 7. So, you can say that when I am giving 0 signal as high, then we can say that this is going to perform the operation addition. So, in that particular case what will happen? This addition circuit will be selected and both the input will be diverted to adder circuit, and we are going to get the result. That means, we need 8 control signal to select any one of these things. But we can reduce the signal over here. Instead of 8 signals, what will happen? We can control it with the help of 3 signals only, because we know that 2 to the power 3 is equal to 8. So, if I am going to use 3 signals, then we can generate this 8 possible combination, because these 3 signals are going to have 8 different possible combination. So, in that particular case what we can do? We are going to use a 3 by 8 decoder. That means, we are having 3 inputs and we are having 8 output lines, and those output lines will be connected to those particular select signal of this ALU. Now, when I am giving say all 0, then what will happen? This is the 0, then this signal will be high, that means, we are going to select the adder circuit. So, this is the way I are going to have 3-bit code, and this 3-bit code is known as my opcode, which is your operation code. So, if it is your 0, I can say that this is your add. When it is your 0 0 1, I can say this is your subtract, like that. So, 0 1 0 and 0 1 1. So, these are the arithmetic operation. So, when this third bit I am going to put as 1, then I can say that I am going to use those particular logic operation. So, now say since with the help of 3 bits I am having 8 different combinations. So, we can use a 3 by 8 decoder to select the appropriate operation. So, this is the way we are going to use our arithmetic and logic unit in our computer, and what operation we are going to perform, that will given by the opcode, which is a binary code. Depending on the combination of the input signal, we are going to select one of the operation, and this ALU is going to perform that particular operation. So, we are going to use an ALU in our computer. So, we can have 8-bit ALU, which can perform operation on 8-bit numbers. We may have 16-bit ALU, which can perform operation on 16-bit numbers. Now, I have already mentioned that we are having 2 type of digital logic circuit. One is your combinational circuit and another one is sequential circuit. I have briefly give idea about the combinational circuit, which we are going to use while constructing the digital computer, but we may have many more other circuitry also. But in this particular course, we are not going to discuss, but just giving you some idea. Now, whatever circuit you are going to have, I think you can analyze it and you are going to get a feeling how that particular circuit will be constructed or implemented. Now, second class of circuit is your sequential circuit. So, in case of sequential circuit, already I have mentioned that the current output depends on some previous output also. So, that is why it is a combination of your combinational circuit as well as some storage. So, this is a combinational part of my sequential circuit. Depending on input, we are going to get the output, and some of the output is going to act as an input for the next time. So, those output we need to retain it, and we are going to say this is the some sort of storage element we are having. Now, this storage will come, whatever we have stored or retained, that will come as an input to the circuit, and the next output will depends on the current input as well as the previous output. Now, when we are talking about these things, current output, previous output, that means it is related to time. So, this time will be maintained by a timing signal, which is we call this is the clock signal. So, in every clock signal, say whenever this clock is coming, then at that particular point this circuit is going to perform its operation. We are having the input signal, we have the previous output. Now, this circuit is going to work say when this particular clock is high, and accordingly it is going to give me output, and when this clock is low during this time, this circuit is not going to behave. So, we can just think in that particular way. So, when this is the one state, this is the second state. Now, this output of this particular present state depends on the output of the previous state. So, it will be controlled by a clock. So, for that we need the storage. So, when we are going to look for your sequential circuit, basically we have to see how we are going to retain the information, that means the storage element. So, for that we are having a storage element called SR latch. S stands for set, R stands for reset, set and reset. So, it will be implemented with the help of your NAND gate. This is a NAND implementation and this is a NOR implementation. Now, how it is going to behave, just I am going to explain one of this particular table. Say when S is equal to 0 and R is equal to 0, then I am having two output Q and Q bar. One is the complement of the other. So, S means set. When S is equal to 1, it is going to set the output to 1, Q to 1, and then Q bar is equal to 0. And when 0 1 combination is there, then it is going to reset this particular circuitry, and we are going to have this is as 0. And now, when 0 and 0, then what will happen? What is the output over here? Now, here you just see that I am having two combinations, 0 0 is your 1 0 and 0 0 is your 0 1. So, see output varies. When I am giving both input as 0 0, at some situation I am going to have 1 0 and in some situation we are going to have 0 1. So, it depends on my previous configuration. So, if after 1 0 combination, if I am giving 0 0, then what will happen? It is going to retain the previous output, 1 0 will be retained over here. That means, I set it, and after I keep this signal as 0 0, then I am going to retain this particular output forever. Again, when I am going to give 0 1, I am resetting it. So, we are getting 0 1 output, and after that if I am giving 0 1, then what will happen? We are going to retain this particular information. So, this is basically the present output depends on my previous output. So, that is the way we are going to retain our previous information. So, this is a single bit SR latch. So, we can go for more number of bits. So, we are just going to replicate these things. Now, you just see how it is going to work. When it is your 1 0, say I am giving 1 over here. So, as soon as I am giving one of the input is your high, then what will happen? OR gate is going to give me output high and NOR gate is going to give me output 0. So, it will be 0. Since there 0 is fed back to this particular point and say reset I am going to put as 0. So, when both are 0, then Q will be 1. So, this is your 1 0. Similarly, you can analyze what will happen in case of your 0 1 also. And in case of 0 0, it is going to retain the previous input. You can see when I put both are 0 0, it depends on my this output only. So, this is SR latch, but here we are having one problem when we give 1 1 combination. Okay. So, it is we are saying that 1 is the complement of other, but because if we give both as 1 1, then what will happen? It is going to get 0 0. So, it is undefined we are saying, but we do not have any problem. But after 1 1, if we give 1 0, then we are going to get 1 0. If we give 0 1, then we are going to get 0 1. But what will happen after 1 1 if we are going to get 0 and 0 0? Because in that particular case 0 0 may turn up to be a 1 0 or 0 0 may turn up to be 0 1. So, what we are going to get? So, this is the problem, and we said this is the race condition, because why we will say race condition? We are using 2 NOR gate over here. and every gate are having some propagation delay, but it is not possible to fabricate 2 gates with the same propagation delay. There will be a fraction of differences, one will be slightly faster than the other. So, after 1 1, whether we are going to get 1 0 or 0 1, it depends on the propagation delay of these 2 gates. Whichever is faster, it is going to act first, and accordingly it is going to set the output. So, that is why we say this is the rest condition, and we should avoid this particular 1 1 combination, otherwise we do not have any problem. So, to avoid these things, what will happen? We are going to have a SR latch with control input. Here we are going to put an control input, and this circuit is going to work when this control input is 1. When it is 0, that whole circuit is not going to perform. There will be no sense, that means whatever information we have, it is going to return over here. If q is 0, it will remain as 0. Now, what will happen? Now, in that particular case, whenever we want to set it, then we are going to give 0 1 over here. Whenever we want to reset it, I am going to give 1 0 over here, and if we are going to give 0 0, then it is going to return it. But when I am going to apply clock, at that particular point, we will try to avoid this giving 1 and 1 combination at S and R. That is the way we can control it with the help of this control signal. So, this is the basic building block of our latch, SR latch, and with the help of this thing, we can construct some of the other latches or other flip flops. So, when we talk about it is clock, then we use the term flip flop also. So, when we talk about latch, then at that particular time that control clock signal is not there, but when it is clock, then we say these are flip flop also. So, we can construct those particular flip flop with the help of this basic SR latch with control input. Now, in this particular case, what will happen? You just see that here we are having 2 input SR R. So, in that particular case, what happens? What we are doing? One is the complement of the other. So, if it is this 1, then other is your 0, and if it is your 0, then other is 1. So, that combination 1 1 is totally avoided. Now, it will not go to any race condition. And if you look into the behavior, then what will happen? When control input is not there, then whatever may be the D value, then it is going to retain my previous input. So, when D value is 0, then output is 0. When D is 1, output is 1. Basically, it is D is 1, output is 1, D is 0, output is 0. You can analyze it with the help of this particular table. And in that particular case, we said this is a D flip flop. Why you are going to say D flip flop? You just see the behavior. Whatever input we are giving, it is coming as an output in the next stage. So, after some delay, it is appearing as my output. That means, when clock signal is arriving, so we are giving a continuous clock signal. So, when clock signal is present, at that time whatever input we have, it will be transferred to the output Q. And during this time we are doing nothing, again this point we are doing it the information. So, whatever input we are giving, it is reflected in output with some delays. These delays depends on the propagation delays of the component. That is why we said this is a D latch or D flip flop or delayed flip flop. This is one. So, another one we are having JK flip flop. So, again it is constructed, we can construct it with the help of D flip flop. Here we can provide this J and K. So, just see the behavior. It says that if J and K are 0 0, there is no sense of the output. If it is your J is 0 and K is 1, basically K represent for reset, we are resetting it. So, output is 0, and when it is your 1 0, J stand for your set, that means we are setting it, output is 1, and when it is 1 1, at that particular point the output toggles. If it is Q, then it will become Q bar. So, if output is 0, then it will become 1, if output is 1, then it will become 0. So, this is another building block we call JK flip flop. So, we can control it with the help of this input signal J and K, and along according to the values of J and K, we are going to have the output over here. So, one is your no sense, one is your toggling the output, and other two combination, one is your set, other one is your reset. So, we can retain the information at the output till the next clock arrives. So, we are having a continuous clock over here. So, another one we are having T flip flop, which is your toggle. So, this is very simple from constructing from JK flip flop. You just see that when both the input is 1, then what will happen? It toggles basically. If output is 0, then it becomes 1. When it 1, then it becomes 0. So, we tied this particular j and k to one single input. So, if t is 0, we do not have any change in the output. When t is 1, then it basically toggles. So, this is another building block. So, these are the storage element flip flop. So, basic one is your RS latch, but from latch we can construct our flip flop, and basically we are going to have 3 basic flip flop. One is your D flip flop, second one is your JK flip flop, and third one is your T flip flop. With the help of this flip flop, we can construct some other flip flop also. So, we are not going to discuss about it, but with the help of this flip flop, we can now construct our storage element. Now, along with that, we are having 2 more signals called, one is preset and one is your clear. So, these are basically asynchronous input. When we are coming about asynchronous input, that means we are having another type of input also, which is known as your synchronous input. So, in case of synchronous input, what will happen? Say here, when I am changing my input j and k, when output is going to get changed, it will be synchronized with the help of a clock signal. When there is a clock signal arrives, then during that time output changes. So, this is related to this particular control clock, and we said this is the synchronous behavior. Now, if you are using 2 flip flop to keep 2 bit of information, if it is a synchronous circuit, then what will happen? Output is going to get changed simultaneously when the clock signal is there. And in case of asynchronous signals, what will happen? As soon as my signal is coming, irrespective of the clock signal, it is going to change the behavior of the output. Just say that I am going to consider about a longer clock period. So, in that particular case, that in case of synchronous, if this clock is there, then only output is going to get changed. But if some input is coming over here, there will not be any change in output. But in case of these 2 asynchronous output, preset and clear, irrespective of the clock signals, it is going to take immediate effect, and accordingly it is going to change the output. So, these are used to either set or clear this particular flip flop. So, we are storing some information, but at some point of time I want to clear it. Then as soon as I give the clear signal over here, then what will happen? The output will be 0. It is clearing the information. And as soon as I am giving the preset signal, basically we are going to set the value to 1. So, we said this is the presetting the flip flop. So, it is irrespective of the clock signal, whenever this preset signal will come, what will happen? The Q bit will be set to 1. So, that is why we are saying it is asynchronous flip flop, because while constructing our circuit, sometimes we will be needing this particular clearing the information or setting the information to 1. Now, with the help of this particular flip flop, we can construct some of the basic building block. One of the basic building block is your resistors. What is a resistor? Basically, resistor is a device, electronic circuit, where we can store information. So, in that particular case, if I am going to say that I am having a 4-bit resistor, then what will happen? We are storing 4 bit of information, and whenever required, we are going to take it to the output line, say A0, A1, A2, A3. So, we are storing some information. Now, what is there in this particular register? Basically, we are having 4 flip flop. According to our requirement, we are storing the information in the flip flop, and after that, whenever is required, we are going to take this particular information. So, here we are going to talk about an universal shift register. So, basically, this is the register. With the help of this register, we can store our information and we can perform some operation, and we can take out our information whenever it is required. So, it is giving a diagram of 4-bit universal shift register. So, what happens basically, it is having 4 operations. One is your shift register. We can shift the information either towards right or towards left. So, one is your left shift, second one is your write shift, and another information we are having parallel load. We can load the information parallelly. So, 4 bit of information we can load it parallelly, and whatever information we are having, these are available always in this particular output lines. So, these are basically D flip flop, these are the Q point of this D flip flop. So, these are always available. Now, you just see what is there basically. Now, I am saying that we are having 3 operation, left shift, right shift, parallel load, and along with that we can say that no effect. So, whatever information we have, always these are retained. So, for that now we are having 4 operation you need to perform. So, for that what happens, we are using a 4 by 1 max. Depending on the input scenario, we are performing this particular, giving one of the input as an input to this particular D flip flop. So, say it is 4 by 1 max, we are having 4 input selection, and we are going to select one of this particular input and putting in into the output of max. And how we are going to select it? We are going to select it with the select line S0 and S1. Now, just I am going to consider one particular input. You just see this particular signal. This output is directly connected to 0, this output is connected to 0. So, all the outputs are connected to 0. That means, whenever I am giving the select line as 0 0, these input lines will be transferred to this output lines of the max, and that will go as an input to the D flip flop, and whenever clocks arrives, then what will happen? That will be transferred to these things. That means, you see that we are retaining that information over here. That means, that no effect will be given by this particular control signal S0 and S1. Now, just consider one particular things. You just see about this particular input 2. Now, what is happening? In this particular things, we are giving a new input, and whatever information we have over here, this is coming as an input to the next D flip flop. The output of this one is coming to as an input of these things. Now, what will happen? Say, initially, if I am storing say 1 0 1 0, say we are retaining it. Now, whenever I am giving the input as 1 0, that means 1 0, and I am selecting this particular 2 signal, then what will happen? Whatever input I am giving, it is coming to this particular input signal, and it is available over here. Now, from A0, whatever output is there, it is coming as an input to the next flip flop. So, now this is basically transferring information from A0 to A1, A1 to A2, and A2 to A3. So, basically 0 will come over here, 1 is come over here, and 0 will come over here, and this one we are not keeping anything. So, this is 0 1 0, that means these 3, and whatever input I am giving, so I am giving input 1, then it will become 1. So, in that particular case, say whatever we are having, we are shifting this information towards left. So, it is now new information become this one we are not storing anywhere. So, it is shifted 1 bit towards left, and the new input is coming through this particular serial input. So, this 1 0 combination is going to give me your left shift operation. Similarly, we can have the right shift also. Just see the behavior, and you can find out the control signal. And whenever I am going to give 1 1, so basically that left shift we are going to get at your 1 0. So, here right shift will be 1 0. Now, when you give 1 1, then what will happen? You just see that this third input line of max will be transferred to the output of the max, okay? And when clocks arrives, then that will be stored in this particular D flip flop. So, that means we are parallelly loading this particular input to this particular register. So, that is why we say this is a universal shift register. We can perform the shift operation as well as parallel load, or we can retain the information also as long as we required it. So, this is a 4 bit. So, if we need an 8 bit, then what will happen? Now, we can use 8 flip flop and 8 max. So, to store our information in our computer, in our processor, we use such type of register. Another one, it is called counter. So, this is the ripple counter we are having. Now, what basically it is having, you just see that we can say that this is the continuous running clock, and as soon as the clock is coming, then what will happen? The output is going to get changed. Now, what basically it happens that here we are going to put 1 as J and K for all the flip flop. That means, that J K flip flop is going to act as an toggle flip flop, T flip flop. Now, what will happen? Say A, B, C, D. Initially, say we are resetting it, say all are 0. Now, what will happen? When this clock arrives, then what will happen? Input is going to get changed over here depending on this particular behavior. So, as soon as this clock arrives, then what will happen? That A is going to get toggle. So, it will become 1. Since this is remain as 0, so all will remain as 0. So, this is the behavior. You just see that when clocks arrive, that A is going to get it from 0 to 1, but it will remain 0. Now, whenever its next clock is coming, you just see that again it is going to get changed, but now since this clock is available now this B is going to get changed. So, now when this signal is coming over here, then I am going to get 0 0 1 0. Similarly, when this is coming now 1, it will remain as 1. So, there is no change in the C block. So, it will remain as 0 and next clock coming it is 1 1. So, we are going to have such type of thing. So, this is the number if I am going to look for this thing. So, this is 0 1 2 3. So, it is going to have the going to give us the counting effect. We can count our numbers. So, this is another circuit. So, in details we are not going to discuss it, and why you are going to say this is asynchronous, because all are not controlled by a same clock signals, they are going to control by different clock signals. So, this clock is coming out from the first flip flop, and when this signal is going to get it changed from say 1 to 0, then this flip flop is going to get affected, it will go from 0 to 1. So, all are not synchronized by the same input clock, they are synchronized by different, or they are operated by different signal clock signal. So, that is why I am going to say this is your asynchronous counter. Similarly, we are having that synchronous counter. You just see that now here we are giving the same clock to all the flip flops. So, again it is a 4-bit counter. I can say that A0, A1, A2, A3. Now, you just see how we are setting J and K over here. Depending on that, you are going to get the behavior. So, initially if all are 0, then when first clock comes, then it will become 0 0 1. Next clock pulse, it will become 0 0 1 0, then 0 0 1 1, like that it will go, and finally, all are will be 1, and again from 1 it will go to 0. You can analyze this particular circuit, and we are saying this is your synchronous counter, because all the flip flops are controlled by one common clock. And I think here you can see these things, that some figure 6.12 is coming. Basically, I am taking this particular diagram from a book of digital design by M. Morris Mano, and this circuit counter circuits are explained in the chapter 6. So, you can go for this particular chapter if you want to have some details of analysis of this particular counter. But here we are just simply talking about the informative purposes only. In knowledge level, we are going to use counter when we are going to build our computers. So, this is the some blocks of your counters. Now, what will happen? You just see that here I am having some of the input signal. One is your up down. So, it is a counting up or counting down. Okay. Along with that, we are having some input also. That means, with the help of this input, we can preset this particular counter with the help of this particular preset enabled. Now, just say that if I am going to give set, these are J1, J2, J3, J4. Now, in that particular case, say if I am giving 1, 0, 0, 1, and I am enabling this particular preset, then what will happen? We are going to set this particular counter to 0, 1, 0, 0, and these output are basically these are the Q bits, these are the outputs. So, in this counter we are going to get output as your 0, 1, 0, 0. at that particular point, I think you are having slight idea about binary number system and decimal number system. So, in that particular case, I think this is your decimal 5. Okay. In next class, we are going to see about more details about these things. Now, when I said that this is an up counter, then what will happen? It is going to count from 5, 6, 7, 8 like that. In case of up counter, when we set it as down counter, then it is going to do the countdown. Basically, it is going to 5, 4, 3, 2 like that. This is a down counter. So, that means we can preset the counter to some initial value. From that, we can count up or we can count down also. Along with that, we are having another one called control signal called binary and decade. I think you know what is decade. Decade stands for a particular decade, that means it is 10. So, if it is a say binary counter, it is a 4-bit counter. What is the different combination we are having in 4-bit? This is your 2 to the power 4, which is equal to 16. That means, it will count from 0 to 15 and come back to 0. That means, we can have a counter for 16, 0 to 15 and coming back to 0 when we are going to use as a binary counter. But in case of decade counter, what will happen? We are going to restrict the count to 10 only, 0 to 9. When as soon as your 10 will be coming, then again it will reset to 0. That means, we can count the decimal number 0 to 9. So, what will happen? It will count from 0, 1, 2, 3 like that. It will count up to 9. Then what will happen? When after 9, in case of binary counter, it should go to 10, but now here again it will be 0, 1, 2, 3 like that. So, when we set to as a decade counter, we are going to count 0 to 9 again reset to 0. But when it is a binary counter, then we are going to count from 0 to 15, then again 0. So, this is a counter that we are going to use in our circuit. So, here what will happen? We have discussed some of the building blocks that will be used in our computer. And what is those building blocks? We are having two type of building blocks. One is your combinational circuit, second one is your sequential circuit. In case of sequential circuit, flip flop is the main building block. With the help of one flip flop, we can store 1 bit of information. So, if we need to retain more bit of information, then we are going to use more flip flops. And two basic building blocks we have discussed over here. One is your register. Registers are nothing but a storage element. We can store our information. With the help of an n bit register, we can store n bit of information. Another one counter, it is basically going to count a sequence from 0 to n. So, if we are going to look for an n bit counter, then what will happen? It can count from 0 to 2 to the power n if it is in binary counter, but that counter can be configured for other counter also, like that we have discussed about the decade counter. Okay. So, these are the basic building blocks that we are going to use while going to construct our computer. Now, just see some of the test item or questions. So, first question I am saying that what are the main characteristics of digital system and analog system? So, already I have explained about it. Digital means discrete, it is going to work on discrete signal. So, we have mentioned some of the objectives. So, this question is related to the objective 1 of this particular unit. Second question I am talking about design a 4 by 16 decoder with 2 by 4 decoder having enabled signals. This is meeting the objective 2. So, construction of some digital building blocks. So, already I have explained one example. I think I am constructing a 3 by 8 decoder with the help of 2 by 4 decoder. Now, we are asking to construct 4 by 16 decoder with the help of 2 by 4 decoder. Just first you think how many decoder will be needed to construct this one. You have to correct one. If you are going to get the right number, then drawing diagram is a very simple one. So, you have to find out how many 2 by 4 decoder will be needed to 4 by 16. So, 4 4s are 16, but I can tell you that it is not 4 2 by 4 decoder. Okay. This is not the correct answer. Third one I am talking about explain the importance of clock signal in digital system. So, this is objective 1 and 3. Basically, in case of your sequential circuit, it may be synchronous and asynchronous, we need the clock signal. So, you just look for the importance of this particular clock signal when we are going to design any digital system. question 4 I am giving like that, consider an ALU with 4 arithmetic operation and 4 logic operation. How many control signals are needed to work with this ALU? I think I have already explained these things in my lectures. You can go back to that particular portion and you can get it over there. Question 5, indicate the use of a multiplexer. So, you know what is multiplexer? We are having several signals. Now, we want to select one of them only. That can be done with the help of multiplexer. Like say in question 4, this is a use of decoder. With the help of decoder, we can select one of those particular operation. Now, you just think where you are going to get the use of multiplexer, that we are having several input and we are going to select one of these things. I think already in our lecture, we have used somewhere in multiplexer, maybe do you remember it? While going to look for the designing of our universal register, I think we have used multiplexer over here. Now, you look for some other example where that multiplexer will be used. So, with that I am going to wind up this particular unit. Thank you very much.